So before we get into the introduction to the derivative, let's just look at really quickly at another AP question of the day. We've got a table of values, and the question is which limit is supported by that table of values. So pause the video, make your decision, and then come back for the explanation. Okay, so first of all, we need to look at what the x values are doing. The x values are getting closer and closer to 1, so we can go ahead and eliminate the first answer choice and the last answer choice. Now, to decide between the 3 that are remaining, we need to, well, there's a couple things we can do. The middle one, 1 from the right equals 1, that doesn't even make sense because the y values are definitely not approaching 1. So we're between either the two-sided limit or the limit from the left. We'll look at the x values. We only have x values to the left of 1, so it has to be the 4th choice. Okay, so let's look. This is an excerpt from a book called The Cartoon Guide to Calculus. And so I'm not going to read through it. I'm just going to kind of slowly scroll. So you can pause the video. I want you to read through it, and I want you to think about what it's trying to get at, because speed, velocity, and change are the driving forces of why calculus came into existence. So you'll see the names that were mentioned in the Big Bang Theory clip. So check that out and see how calculus started. So we're going to take that idea and we are going to begin the idea of being able to find the instantaneous rate of change of a function. So we're going to start with a little illustration here. Let's start by going all the way back to slope. Slope is the average rate of change. You've got to get used to that concept because they like to use the terms average rate of change in calculus, and when you see that terminology, you should automatically think, I'm calculating the slope. Okay? It could also be the change in y or the change in x. Obviously, we use the variable m to represent slope. All those things there are synonyms. You've got to understand those are interchangeable pieces. So let's look at, we've got a parabola here. Okay, we've got a parabola, and we're going to talk about this line that is drawn through this parabola. This line is what we call a secant line. Okay, a secant line is a line that is drawn through any 2 points of a curve. Okay, a secant line is drawn through any 2 points in a curve. So we can see this one point at 2, 3, and then another point here at 4, 4. Okay, so the line is drawn through those 2 points. It's what we call the secant line. We could have put it through 4, 4 and 8, 0. Okay, it would have been a completely different line, but that's another secant line. You can have infinitely many secant lines on a curve, but the premise is a secant line passes through 2 points on the same curve. So if we need to find the slope of this secant line, obviously I'm hoping that y'all are familiar with the equation y2 minus y1 over x2 minus x1. okay, the change in y, delta y over delta x, the change in y over the change in x, delta, that triangle meaning change in, if you've never heard that terminology or seen that symbol before, okay, the triangle means delta or change in. Okay, so some things that we need to be familiar with. Okay, I've got that first point labeled. We obviously see that it's 2, 3, but let's label it in general terms. Okay, it's labeled in blue there as x, f of x. Remember, f of x is just a fancy way of saying y. Okay, that's the y value when x is, in this case, 2. Okay, let's say that we move this distance right here, the change in our x, okay, we can physically see that we moved 2 units in the x direction to get from the first point 23 to the point 44. But let's try and keep this in general terms here, okay? So we've got x and f of x representing our first point. So our second point here, if we want to represent that in general terms, if we start at x, we add delta x to that. Okay, we started at x and we added that delta x, that change in x to it. Okay, we went from 2, we ended up at 4. The delta x was 2. Okay, I'm trying to give you a concrete example of where it started. Okay, and then as far as our y values, well, our y value is going to be the f of x plus delta x, the y value at this x value, x plus delta x. So if we were trying to find the slope using that terminology there, okay, let's use the slope here. We have the second y value minus the first y value over the second x value minus the first x value. So we can't simplify anything in the numerator in the form that it's in right now, but we can cancel those x's right there. So all we're left with in the denominator is delta x. Okay, so that's another way. I'm going to run out of room over here, but maybe I can fit it in. This is, there we go, I squeezed it in. That is another equation or formula for the slope of this secant line. Okay, you may also see them, instead of using a delta x, they may use an h. Okay, so same premise, we started at x, we moved h units. So here is what our second point would look like. So if we do that slope, we've got f of x plus h minus f of x over x plus h minus x. The same thing happens. The x's cancel. And we end up with just h in the denominator, just like with the delta x, okay? It's the same thing, it's just sometimes they use delta x, sometimes we'll use h. It just depends on the scenario. You need to be familiar with both. So, well, what's the whole point in having this secant line? Okay, well, think back to the cartoon. The cartoon was talking about, well, when that delta x gets really, really small. So say I move this over. Say I move this second point. I'm going to move it closer to my initial point. And if I were to draw a line through there, and I'm going to cheat and use an actual straight line, okay? If I were to draw a line through those 2 points, and I didn't get it quite at the right slope, so I'm going to move it. Okay, if I draw a line through those 2 points, notice how the line is almost exactly on top of the curve. Okay, it's really, at this point, there's such a small difference that you really can't tell a difference. And that's what happens. The closer and closer that this second point gets to the original point, the closer and closer the slope of this line becomes to the slope at this specific point on the curve. Okay, Now, we can't find the slope of a curve because it's not a straight line. We only find the slope of straight lines. But it's this concept of there is this, what we call tangent line. Okay, this is what we would call the tangent line. And the tangent line is different from the secant line. The secant line goes through 2 points on the curve. The tangent line touches the curve at 1 point, at only 1 point. It can't touch the curve anywhere else. Okay? It can't touch the curve anywhere else. Well, technically it can, but it's only supposed to touch where we're talking about. It's only supposed to touch at one place. It doesn't. We don't use another point on the curve to create it. Okay, and the idea is that it's perpendicular to the curve. Okay, that tangent line is supposed to be perpendicular to the curve. Okay, so these are all very important concepts that we need to be storing in our mind about the secant line and the tangent line. Okay, so the secant line represents the average rate of change. Okay, I'm going to add that to my list over here as well. Average rate of change, because it's the slope. The tangent line is what we call the instantaneous rate of change. Because it's the slope at 1 point. It's not the slope through 2 points. It's the slope at that 1 point on the curve. Okay, kind of a weird concept, so you may need to, this is all we're going to cover right now. We're not going to get into actually doing anything with the formula until next week. So I just want you to wrap your mind around all this vocabulary and around these two ideas of the secant line versus the tangent line, and how we go from the secant line. That delta x, or that h, gets smaller and smaller. We get closer and closer and closer. Those 2 points become closer and closer and closer until essentially we're just talking about at that one specific point. Okay? But I do want to share this idea with you. Okay? This is the limit definition of the derivative. Okay? So we're transitioning from limits to derivatives. Our second big idea in calculus, but we're still using the idea of a limit to get there. Okay, so here with this, you've got to know this. Okay, you have to know this because they do expect you to recognize this on the exam. So the derivative of f at some x is given by, now we have several different notations. The first one is m with a little subscript of x. Well, m is slope, so that's the slope at x. Okay, or we use the notation f prime. That's the f with the little quotation mark there. We read that f prime of x, and f prime represents the derivative of the function f of x. Okay, here's the limit definition. As the limit as delta x approaches 0, so as the distance between those 2 points gets smaller and smaller and smaller, that delta x is approaching 0. The distance between those 2 points is getting smaller and smaller and smaller. Okay, the derivative can be found by manipulating this formula right here. F of x plus delta x. That means we're going to have to take this expression right here, x plus delta x, and plug it into the function f. Okay, and then we subtract just the plain function at f, and then we divide the whole thing by delta x. And the reason for that is because what I just showed you. That's the slope formula in general terms for any function. So we're finding the limit of that as delta x gets closer to 0, and then we're finding the slope of that tangent line. Okay, that's going to give us the slope of the tangent line. Now, obviously, this only works if that limit exists. Okay, there are going to be some places where we cannot find the derivative of a function. So, for example, if you have a discontinuity, if you have a hole, if you have a vertical asymptote, you can't find the derivative at those places because your function is not defined. But as long as your function is defined, and then we'll run into a couple of other scenarios that we'll talk about later where the derivative can't be found. But in general, this is how you find the derivative of the function, which is synonymous with the slope of the tangent line, okay, which is synonymous with the instantaneous rate of change. You got to be familiar with those terms and the fact that they are interchangeable. There are a few other notations for derivatives. The most common are the first three, f prime of x, okay, that's the derivative of that. All these refer to the derivative, okay, but it just depends on kind of what notation is being used. So the first one's f prime of x. The second one, we just read it, dy over dx, and that's the derivative of y with respect to x. That will come more in handy when we do some application problems, because we're not always taking the derivative with respect to x, which I know doesn't make any sense right at this moment, but I'm just planting a little seed in your head. Sometimes that variable on the bottom will change, okay? And then we've got y prime. So if our functions is labeled as y equals 3x squared minus 4x, okay, then its derivative would be y prime. If it was f of x is equal to 3x squared minus 4x, then we would use f prime. It really just depends on the notation that they use. And then the last one is I don't know that I've really ever seen it except in the textbook on a rare occasion. It's a capital D with a subscript of x and a y in brackets. It also means the derivative of y with respect to x, but like I said, it's super uncommon. Okay, so just be familiar with these concepts. That's all I need you to worry about this week. And then starting next week, we will get into actually calculating and finding some of these derivatives.